Okay, so we are finishing up this section. So let me just kind of flip back a page here. So again, this was 7.2 and 7.4 together, and we already covered 7.2, which was the exponential equations. So now we're moving on to log equations. So what is a logarithmic equation? It's an equation with a log expression that contains a variable. That's simply all it is. So an equation with a log expression that contains a variable. And just like there was two different types of exponential equations, there's two different types of log equations as well. So where you have a log on both sides of the equation, so like you see here, you have log base b equal, or log base b of x, log base b of y. You just simply have that x equals y then. So pretty similar idea. If you have the same log with the same base on both sides of the equation, you simply drop the logs and then you just set these equal to each other. But if you only have one log in the equation, the way it's kind of explained over on the right-hand side is a little different than the way I explain it, but if you only have one log in the equation, you're just basically going to represent the log as an exponential. So you just do that little swooping motion that I've showed you guys before in the past. So it's simply going to be the base of log, raise this exponent, and it equals whatever x may be. Okay, so you just simply want to swoop it around, and that's exactly what this is over here. So your end result is just going to be that x is equal to b to the a power. Okay, so those are your only two options. Keep in mind, though, you might be seeing a lot of the properties that we emphasized back a couple sections ago. So we are going to be using and applying all those properties today. Okay, so as an example, in example 1, I already see one property right now. Okay, if you have a number in front of log again, you got to push it back to be an exponent. So this is really log base 7 of n equals log base 7 of 8 to the 2/3. So I push it back as an exponent. Next thing is, what is 8 to the 2/3 power? So if you actually calculate that, you'd have log base 7 of n equals log base 7, and 8 to the 2/3 power should just be 4. And now the last thing is, well, since I have the same log on both sides, so if you notice, log base 7, right? If you have the same log with the same base on both sides, you drop the logs all together, you set n equal to 4, and that's obviously your solution, n equals 4. Okay, so we're already done. That's it. So number 2, similar idea. What I'm going to do first, though, is push that back as an exponent. So I have log base 10, 27 equals log base 10 of x cubed. Okay, next, again, you see the same log with the same base on both sides. So I'm just going to drop the logs all together, set 27 equal to x cubed. And now how do we actually solve for x? You take the cubic root of both sides. So when I take the cubic root of 27, I should get 3 as my final solution, and that'd be it. Okay. The next one, number 3, again, I see a property on the left-hand side. Combine these two logarithms to be one log by multiplication. So the fact that there's a plus sign in between, I got to multiply. So this would be log base 6. I'm multiplying 2c and 8c. So that's 16c. And the right-hand side stays the same. Okay, so using our properties, again, combining by multiplication since there's addition in between. Next thing, since you do have the same log on both sides, log base 6, drop the log, set 16c equal to 80, and now just simply divide both sides by 16. So you should get, for c, it should come out to be exactly 5. 80 divided by 16, c is going to be 5. Okay, so we've seen the first examples, right, where you have a log on both sides of the equation, same log on both sides, but for example number 4, you only have one log in this equation. So what I'm going to do for this one, since there's only one log, swoop it around. I'm saying that 5 to the 8th power equals x to the 4th power. Okay? Next thing is, well, what is 5 to the 8th power? So if you type in 5 to the 8th power, you should get 390,625 equals x to the 4th. And now to actually solve for the x, since it's to the 4th power, I'm just going to take the 4th root of both sides. But since it is an even root, you also have to remember this comes out to be plus and minus. And when you type in the 4th root of 390,625, you should get 25 as your solution. So same thing for number 5. Since there's only one log in this equation, I got to swoop it around. So I'm saying that 6 to the negative 1 equals 2x minus 1. So 6 to the negative 1, that's just 1/6. equals 2x minus 1. Subtracting 1/6 on both sides. So if I subtract 1/6, or rather, I'm trying to get x by itself. So I'm going to go ahead and add 1 to both sides. So if I add 1 to both sides, that would be 1 and 1/6 equals 2x. So 1 and 1/6 though is the same thing as 7 over 6. I'll just go ahead and write that as an improper. And now dividing both sides by 2. Well, if I'm dividing by 2, I'm essentially multiplying by a half. And I get 7/12 is my solution. Okay, for example number 6, first thing, combine these two logs to be 1. So on the left-hand side, make those two logs just one log, a single log, by multiplication. So this would be log base 12. We're multiplying x and x plus 1. So that'd be x squared plus x, then equals 1. Okay, so multiplying x and x plus 1 is x squared plus x. Again, since there's only one log in this equation, you got to swoop it around. So 12 to the first power equals x squared plus x. And hopefully we know what to do from here. Okay, as soon as you see an x squared, that definitely means we have to factor. So to factor this, I'm going to bring the 12 over to the other side, making this x squared plus x minus 12 equals 0. Factoring would be positive 4 and negative 3. And then solving it, we get negative 4 and positive 3 as our two possible solutions. Okay, however, when you plug these answers back in, negative 4 actually does not work. Only positive 3 works. And the dead giveaway, so when you plug this back in, negative 4, this can never be a negative number. It is impossible. So when you plug negative 4 back in, you're going to have log base 12 of negative 4 for the first logarithm, and then log base 12 of negative 4 plus 1, which is going to be negative 3. Okay, so again, it can never, ever, ever be a negative number. That's in the definition of being a logarithm. So just make sure you check your answers. Okay, the reason why it was okay though, if I backtrack to number 4, so when I plug in, so we got positive and negative 25, right? Well, positive 25 to the 4th power is going to be a positive number. Negative 25 to the 4th power is also technically a positive number. So technically, although the answer itself is negative, when you plug it back into the logarithm, it's technically going to be a positive number once you calculate it. Okay, so that one's not going to be affected. So you just want to check that. Okay, there's going to be, I think, at least one more example of this. So I'll make sure I outline that one more time. So for these next examples, example 7 again, condense these two logs to be a single. So anytime you have two logs on the same side of the equation, you want to condense them to be a single log. How I'm going to condense this one though, since there's a minus sign this time, is we're dividing. So it's x plus 4 over x minus 3, and this equals 3. Okay, so x plus 4 just simply goes over x minus 3. Now, setting this up, so since there's only one log in this equation though, I got to swoop it around. So I'm saying that 2 cubed is x plus 4 over x minus 3, which would be that 8 equals x plus 4 over x minus 3, so that is 2 cubed. Next thing I would do, I'm just going to throw the 8 over 1 and cross multiply. So that would make this 8x minus 24 equals x plus 4. So 8 times x minus 3, make sure you distribute. So that's going to make this, subtracting 1x is 7x, adding 24 would be 28, dividing by 7, x equals 4. And there's your solution. Okay, so similar idea for example number 8, combine these two logs to be 1 by division once again. So that's n plus 1 over n minus 2. All right, since there's only one log, once again, swoop it around. 4 to the first power equals n plus 1 over n minus 2. Again, I'm just going to throw the 4 over 1 and then cross multiply from here. So 4 times n minus 2 makes that 4n minus 8. That equals n plus 1. Solving for n, if I subtract 1n is 3n. If I add 8, that makes it 9. Dividing by 3, I should get 3, and that should be okay. All right, moving on to the next one. So I see two properties here. First one, exponent, move it back, first and foremost, making this log base 8 of 2 cubed minus log base 8 of 4 equals log base 8 of b. So that'd be log base 8 of 8, that is 2 cubed. Put an equal sign, but I meant a minus sign, log base 8 of 4 equals log base 8 of b. Next, combine these two logs to be 1 by division. So that's log base 8. 8 divided by 4 just makes that 2 equals log base a to b. Okay, so I'm done with all the properties. Now it's all about, well, how do I solve this log equation? Since you have the same log on both sides, just simply set these equal. And you already have your answer, b equals 2. Okay? The next one, again, there's a few properties going on. So on the left-hand side, we got to combine these two by multiplication. The right-hand side, first and foremost, push back the exponent. So I'm going to make this a log base 5. Multiplying those would be 120. This would be log base 5, 2 cubed. I'll just go ahead and write that as being an 8. Log base 5 of a. So still combining these two together, again by multiplication. So the left-hand side is not changing, but the right-hand side would be log base 5 of 8a by multiplication. And now since you have the same log on both sides, drop the logs, just simply set these equal. Set 120 equal to 8a, and then dividing both sides by 8 gives you your solution. So 120 divided by 8 should come out to be 15. And there's your solution. Okay, the next one. Left-hand side, combine these two logs to be 1 using my properties, again by multiplication. So that would make this 3x squared minus 5x. And the right-hand side stays the same. So same log on both sides. Drop the logs. Just set 3x squared minus 5x equal to 2. And now solving by factoring. Bring the 2 over. You have 3x squared minus 5x minus 2 equals 0. So let's see, how is this going to factor? We got 3x and x, so multiplying by 2 is obviously 1 times 2. We need negative 2, but a positive 1. So we get two answers here. We get negative 1/3, and then we also get positive 2 as our two solutions. But again, now you want to check them, especially that negative 1/3. That one's kind of standing out to me. So you want to check and make sure that this is not going to be a negative number. But obviously when you plug in negative 1/3, it's going to be. And same thing over here. If I plug in negative 1/3 here, that's going to be 3 times negative 1/3 is negative 1, and then minus 5 is negative 6. So they both come out negative, so negative 1/3 is not your true solution, only positive 2. Okay, that would be your only solution that you got. For number 12, first thing I'm seeing, exponent, push it back. So you'd have log base 4 of the binomial squared equals log base 4 of 11 minus x. So now you got to square the binomial, right? So how you square a binomial, well, you got to FOIL it. X plus 1 times another x plus 1, expand it out, FOIL those two together. So what you should get is x squared, right? And then 1x and 1x makes that 2x plus 1. And that equals log base 4 of 11 minus x. So since we have the same log on both sides, drop the logs, just simply set x squared plus 2x plus 1, set it equal to 11 minus x. And now bring everything over to one side, and then we're just going to factor. So if I add 1x to both sides, I'm going to have x squared plus 3x. Subtracting 11, though, makes that negative 10 equal to 0. Factoring, this would factor into a positive 5, it looks like, and negative 2, resulting in negative 5, and then positive 2 is our two solutions. Again, check them, especially that negative 5. It looks like, let's see, negative 5 plus 1. So that's, yep, so right here, negative 5 plus 1, that's not going to work. That's a no-go, although it should be okay on this side. So 11 minus negative 5, well, that's just going to be a positive, right? Because you're really going to be adding. But negative 5 plus 1, although you're going to be squaring it after the exponent, the key thing is the initial problem, the original problem. If this comes out to be a negative, that's a no-go. So that one's not going to work. Okay, only positive 2 is your true solution. So for number 13, next example, again, first thing I see, exponents, push back the 3, push back the 2. So we have log base 2 of x minus log base 2 of 5 cubed equals log base 2 of 10 squared. So that's log base 2 of x minus log base 2 of 125, that is 5 cubed, log base 2 of 100. Next, combine these two logs to be 1 by division. There's a minus sign in between, so that's log base 2 of x over 125 equals log base 2 of 100. Since we have the same log on both sides, drop the logs, just simply set x over 125 equal to 100, which is technically over 1. And again, you could just cross multiply or just simply multiply both sides by 125, but you get 12,500 as your solution. Okay, and the very last one, again, combine these two logs to be 1 by division. There's a minus sign, so that'd be 100 over x plus 1. Next thing, swooping it around, I'm saying 4 to the first power equals 100 over x plus 1. To solve it from here, I'm going to throw the 4 over 1 and then just simply cross multiply. So 4 times x plus 1 is 4x plus 4 equals 100. Subtracting 4 makes that 96. And then dividing both sides by 4. Let's see, 4 goes into 9 twice, minus 8, so that'd be 16, so that should be 24 as my solution. All right, so you guys have seen it all. Okay, again, don't forget about all the properties. You can definitely see how much those play a big important part in solving log equations. So we got a little bit more over here, a few more examples to go through. So for the next one, number 15, it says log base 4 of y equals 0. Again, how I would solve this one, there's only one log, so just swoop it around. We're saying 4 to the 0 is y. So what is 4 to the 0? Well, that's just 1. So that'd just be my answer. And then 16 again, since there's only one log, just swoop it around. 2 to the negative 2 is n. So what is 2 to the negative 2? That's just 1/4, and that would be n. And the last one, 17 again, swoop it around. There's only one log, so 2 to the 5th is 4x minus 4. So that'd be 32 is 4x minus 4. If I add 4, that's 36. Divide by 4, and you should get x is 9. Okay, so there's everything all together. Little story problem now. Example number 18 says population. There's a current census that's showing that the population of a city is currently at 800,000, but it's growing at a rate of 1.5% per year. The growth can be expressed by this exponential equation. So this should look familiar because that's basically the exponential growth and decay problems that we did back in the first section. Okay, but P is the population after T years. Find the number of years it's going to take for the population to be 1,000,000. So again, it's starting with 800,000. It's growing every year by 1.5%, which is already plugged into the formula. We want to know how long it's going to take to be 1,000,000. So that's going to be P. The initial amount is 800,000. And then we have 1 plus 0.015. We're solving it for T. Okay, so now that we know how to solve all these equations, this shouldn't be too bad. What I'm going to do first is I'm going to do my parentheses. So if I add those two together, that's obviously 1.015. Next thing I would do then is divide both sides by 800,000. So if I divide 1,000,000 by 800,000, you should get 5/4. So here's where we're at currently. Okay, this is an exponential equation. How do I know that? Well, because my variable is in the exponent. That's the definition of being an exponential equation. So I would want to check and see, can I get a common base on both sides, which I probably wouldn't even attempt that. So I'm just going to go ahead and log both sides of my equation. Again, your exponent then comes forward. So we have log of 5/4 is equal to t times log of 1.015. So all we'd have to do is just simply divide by the log. So we just need to divide those two logs and we will have our solution. So take the log of 5/4, divide it by the log of 1.015, and what you should come out with comes out to be about 14.99. But we'll just go ahead and estimate that to be about 15 years. It would take about 15 years for this population to get to be 1,000,000 if it's starting at 800,000 and growing by 1.5% every year. Okay? Last thing we're talking about today, though, is compound interest using this new formula. Okay, so pretty much everything is the same. It tells you exactly what everything is. So A is going to be the amount in the account after T years. So T is the time, P is the principal, R is going to be the rate, N is the number of compounding periods each year. So how much or how many times are you compounding within this year? Okay, so let me kind of show you how this is done. An investment account is paying 4.2%, so that's the rate. 4.2%, which is 0.042. It's being compounded monthly. That's n. So if it's being compounded every single month, that's 12 times in a year. So n would be 12. I have $2,500. So that's the principal. That's what we're starting with. It's invested in an account. What's the balance going to be after 15 years? That's t. So plugging this all in where it goes. Okay, just using your nifty little formula up there. 2,500 is your principal. You have 1 plus the rate, which is 0.042, over n, which is 12. And then this is being raised to the n times t power. So 12 times 5, or 15, sorry, not 5. 12 times 15. Okay, so first thing I'm going to do, exponent. What is 12 times 15? Well, that's just going to be 180. Okay, and also working out inside parentheses here. So I would probably go ahead and do 0.042 and divide that by 12, and then you're just going to be adding that to 1. Okay, so if I add 1 to that, it's just going to be 1.0035. So we have 2,500, 1.0035 is inside, and again, 12 times 15 is just simply going to be 180. Okay, so next thing you have to do is the exponent. So I want to take this answer, I want to raise it to the 180th power, which I know sounds crazy, but it's actually not that much since it's only 1.0035. And now I want to times that by 2,500. And it comes out to be, so if we just let that money sit there and accumulate all this interest, it would now grow into be $4,688 and about 87 cents. So 4,688. And again, the pennies is 87. Okay, so $2,500, again, 15 years later, if it's being compounded every single month by 4.2%, that's what it would turn into. Okay, and the last one, similar idea. Find the account balance after 20 years, so that is T. $100 is placed in an account, so that's the principal. 1.2%, so that's our rate. And again, that's 0.012 as a decimal. Twice a month it's being compounded. So every single year, 2 times a month. So how many times is that in a year then? That'd be 24 times a year. So n would have to be 24. So plugging this all in. So again, $100. You're going to have 1 plus 0.012 over n. And it's being raised to n times t. So 24 times 20. Okay. So this will be $100. Again, inside parentheses now, I'm going to have 0.012 divided by 24. And now just simply add 1 to it. So it's 1.0005. So we have 100, 1.0005. 24 times 20 is 480. So I want to take that decimal. Again, I'm going to raise it to the 480th power, which is that, and now just simply times that by 100, which just moves the decimal 2 places to the right. It'd be $127.12. Okay, so you can see, if you don't have a great interest rate, 1.2% after 20 years, if you just let $100 sit there and it gets compounded not just once a month, but actually 2 times a month, it only turns into $127.12. Okay? So there you go. There's your last lesson for today. Per usual, if you do have questions, don't hesitate to ask any of your teachers. Come by for tutoring. Okay, watch this video as many times as you'd like to, but now we know everything. Exponential equations, log equations, it's all there for you. So have a great day.